Well, I guess my title is something like My Small Bit of MBE History. I'm really delighted to be sitting with all these great pioneers like Al Cho and Tom Foxon and so on and so forth, and sharing what we went through in the early years of learning about MBE. Now, it said in the program that we're going to be telling you how to do things right. And I think what I should say is that good judgment comes from experience, and experience comes from bad judgment. So what I'm going to talk about principally is incidents of bad judgment. I guess that my activities in MBE really began back in graduate school when I became a very skilled glassblower. My research involved making field emission microscopes, and I learned to make them all the way from making the glass to metal seals, fluorescent screens, blowing everything. And that served me in good stead when I got to Bell Labs. Now, a lot of it, I really want to emphasize what it was like at Bell Labs in those days. I think that those were probably the golden years of Bell Labs, but maybe I'm wrong. Maybe it's still as great as it was then. But my first experience was when on the first day of my employment there, I walked down the corridor with my new department head, and all of a sudden an elderly man came out of a darkened room, grabbed a hold of my arm and pulled me in and said, "Come on, you got to see this." I had no idea who this guy was, but I went into the room, and here was a low energy electron diffraction screen glowing in the dark with spots all over it, and he showed me what it looked like when oxygen absorbed on nickel. Well, the man was Lester Germer of the Davison-Germer experiment fame. Lester had one of two lead systems in Bell Labs at the time. Anyway, Lester turned out to be a fantastic man. He became a great friend of mine. We did lots of mountain climbing together. When Lester was in the mountains, he talked about science. When he was in the laboratory, he talked about climbing in the mountains. I could spend my whole time telling you Lester Germer stories because he was really a unique character. But there were a lot of unique characters there at Bell Labs. In Hagstrom's surface physics department, Walter Bratton was still there, who was another character. Walter was known for throwing a tantrum when things in the committee meetings didn't go his way. But he was also a very interesting and helpful person to know. And Bill Shockley came frequently to the labs. He was back in California permanently, but he was one of the best teachers I ever heard. He could give a lecture on something really abstract, and you knew exactly what he was talking about. He was incredible. Bardeen came occasionally. He was a little more difficult to understand. But the point is that there were all these fascinating people around. My next door neighbor, next to my home, was George Smith. And George Smith and Bill Boyle in the 80s developed the charge couple device, CCD, for detecting light that became such an important key for those working in astronomy. So the list goes on and on and on. There was a man who was studying gravity waves, believe it or not. He didn't find any, I have to say, but that's some of the kinds of research that were going on there. It was very academic. On the other hand, and Mort Panish is around here somewhere. There he is. Okay, I'm going to say some critical things here too. The facilities at Bell Labs were terrible. The labs and offices were primitive. They were like the ones that I'd had back in graduate school. there was a gutter that ran around the lab for cooling water to be dispersed. And it was fine when the water was flowing in the gutter, but when it would dry up, the man up above me might do some noxious experiment and pour the stuff down the drain, and I'd get it down in my lab. This is Bell Labs now. You don't. This is, I think, part of the story that you haven't heard before. There were frequent fires. About once a week, I'd come into the labs and I'd see smoke coming out of the chimneys. The safety precautions were dreadful. There was, as far as I know, there was no safety committee. The things that we did, some of the things we did were really hazardous. A lot of people got acid, but one time I spilled a whole flask of acid down the front, and my pants dissolved. And fortunately, I had a lab coat that I could get on, and my technician called my wife, and she brought me another pair of pants, so everything was fine. But anyway, there were these sorts of things going on. Well, one thing I want to emphasize here is that I'm really happy to be here today because I almost didn't make it. We drove up to Portland Friday night so that we could stay over in a motel and catch the early flight out of Portland Airport. And in the morning, the news was all full of the fires burning in Corvallis, Oregon. And it sounded from the description as though they were right where my house is. My house is in the woods on a hill. So I called around and couldn't find anybody awake to answer the phone. Finally, I got a hold of a friend, and he said, no, it was not my house or not my area. It was about a half a mile north or half a mile south of my area. So I was able to get back on the plane, and everything was fine. But I thought for a minute there it was going to be touch and go. So anyway, I'm here. And now getting back to where I was at Bell Labs, the equipment that we had was pretty primitive too. We were mostly using ultra-high vacuum systems made out of glass with mercury diffusion pumps. The same kind of system that Lester Germer and Davison used in the Davison-Germer experiment. That worked because of an accident, you know. The way they were doing the experiment, it wasn't going to work because they were using a polycrystalline filament of polycrystalline ribbon of nickel. And it would have given them, they wouldn't have gotten the diffraction spots. But the vacuum system cracked during bakeout, let oxygen in, the oxygen got onto the nickel, and in the process of cleaning it up, Germer annealed it to the point where the crystal grains grew large enough so that when they did the experiment, they would get diffraction off the individual crystal grains. That's why the thing worked. Point here is that there is accident that happens in a lot of experiments, and we have to take advantage of it when it does occur. The one great thing to say about Bell Labs, though, was the stock room was fantastic. You could go up to the stock room and find almost anything you wanted. I finally built a glass vacuum system with metal seals, with metal flanges to join so I could take it apart. And these were home-built flanges, just perfectly flat. And we used gold wire, annealed gold wire to form the seal. And I could go up into the stock room and get a coil of gold wire and come back in my lab and make rings of gold, and they worked beautifully. And after I'd built, they worked beautifully once, and after I'd built up a stash of used gold O-rings, I'd take them back to the stock room and they'd accept them. As far as I know, there was no accounting for all of this gold that was being used. Anyway, that's a side point. The big surface problem that we had in those days, though, was surface cleaning. With metal, it was, you know, you could heat metal up to the point where things were pretty clean. But semiconductors were a different problem. And the characterization of it, we had no tools for characterizing these things. Finally, we didn't know what was in the vacuum. And in the mid-60s, I did find out that there was a new thing on the market called the quadrupole mass spectrometer. And I really, really wanted to have one because I had just the experiment for it. Unfortunately, Bell was a little bit careful about their expenses. And right at first, they didn't have the $15,000 to buy my quadrupole mass spectrometer. But my laboratory director, a man named John Galt, about whom I'll say more later, came up with a novel idea. He was going to lease this mass spectrometer. And so we got the quadrupole mass spectrometer, leased it, and I started doing some experiments with it. Well, Mort Panish came to me, and he was doing liquid phase epitaxy, but he needed to know more about the thermodynamics of the gallium arsenic system. So he asked if I would measure vapor pressures of arsenic and gallium over gallium arsenide. So I could do that with my quadrupole mass spectrometer. Worked like a charm, and Mort seemed to be happy with the results, and that justified my mass spectrometer purchase, so that we then purchased the thing completely. We quit paying the down payments and bought it. And that allowed me to get started on this experiment that I really wanted to do, which was to measure surface lifetimes. I wanted to shoot a beam of atoms off of a surface and determine what the lifetime of atoms was on the surface. So you make a chopped beam, you fire a chopped pulse of gallium, say, at gallium arsenide, and you look at the gallium bouncing off as a function of temperature. And if we could there it is, okay. That's just a mathematical depiction of what it looks like at 3 different temperatures. But it's a simple first-order differential equation. The solution is straightforward. You get an exponential, 1 minus exponential rise and an exponential tail on the thing. And that's exactly what we found with gallium on gallium arsenide. Furthermore, the enthalpy of vaporization, which you get from the temperature dependence of these curves, agreed exactly with what we'd already measured in the mass spectrometer experiments. So this was behaving perfectly normally. The next slide, please. So I tried it with arsenic. Tried doing the same thing with arsenic. And in arsenic, the behavior was quite different. Now you can see that when I turn the beam on, there's an abrupt rise. There's no decay in the rise, and there's a gradual increase in the arsenic beam coming off just because the background arsenic pressure is getting higher. But then when I turn the beam off, then it comes right back down. So we've got basically square pulses that we're getting. But when there was a little bit of gallium on the surface, it behaved totally differently, and you can see that there is now an uptake of arsenic. It's not bouncing off the surface when there's gallium present. So this suggested that here is a way to make stoichiometric compound films. There'd been people had done a lot of work in trying to evaporate compound semiconductors prior to this. They do such things as putting a gallium arsenide source in a tube and heating it up, and then figuring out that somewhere along the length of this tube, the atoms would be arriving at the surface to make a stoichiometric film. Well, what this showed was that you didn't need to worry about that you could make a stoichiometric film just from these molecular beams. And this was a pretty convenient way to do it. And it suggested then that we should start trying to see what kind of crystallinity we got. Trying to grow films, in other words. So the only way that I could determine what my film crystallinity was like was to take the films down to an electron microscope, and the guy would do a glancing beam diffraction pattern and tell me something about the films. And the results were kind of discouraging because they showed that we generally had twinned films. They were crystalline, but they were twinned and not very good. So we had epitaxy, but we certainly didn't have single crystal epitaxy. About this time, Mort suggested that we should start calling this molecular beam epitaxy, because, well, we're using a molecular beam, we're also using an atomic beam. We sometimes got epitaxy and sometimes didn't. And these weren't really beams. These are really, an atomic beam is really well collimated, and these weren't well collimated beams. But nevertheless, the name is good and has stuck. So that's what we're still using. Let's see, we're running out of time here. I better speed up. About this time, then, John Galt and Mort decided that we really needed to put some more teeth into the effort, and Al Cho was hired from the University of Illinois, which shows the extreme good judgment of John Galt and Mort, and came to work with us. At first, we were given. It was suggested that we might try growing diamond film, and I remember that, Al. We had an old glass system, but we needed diamond substrates. So we walked down from Bell Labs about 2 or 3 blocks, and there was this little building where it went inside. A guy, an older man in a white lab coat, invited us in, and he pulled out a drawer and stuck in his scoop and started scooping out diamonds onto the counter. So we poured through these diamonds, finding ones that were large enough that we could take. I think we spent about $200 or $300, something like that, buying diamonds. We took them back, put them in our system, and evaporated from graphite onto the diamonds. And all that we got was a black scum on each diamond. Well, the problem there, or maybe the problem was, I think the problem was that when you evaporate graphite, you get carbon-8 molecules coming off. So you're already basically putting graphite back onto the surface of the diamond. So that didn't last very long. We canned that. And I think that was when Al had a really good piece of luck. He got Dick Henderson's machine. Isn't this right? Okay. Well, all right. Well, anyway, at some point, Al got a vacuum system that had a high-energy electron beam diffraction gun on it, and was able to do some diffraction studies during growth. And I think that this was one of the absolute crucial points in MBE. It said that the whole thing was going to work. Al can tell you more about the details of that. Well, this was also a time of the Vietnam War, and we were very, very conscious of this. Every day at lunch, we'd gather around a circular table, 8 or 10 of us, and discuss what we thought was happening. And it was kind of a gloomy period of time. Long about then, Mort found that there was a boron nitride manufacturer up in New Hampshire. So Mort and I got in the car and drove up to Lawrence, New Hampshire. It was a long drive, several hours to get up there. And here was this factory on the banks of the Merrimack River. It had an old paddle wheel. The the water would turn the wheel and generate electricity. I think they were still using it. Anyway, they told us how they made boron nitride. Take boron trifluoride and pyrolyze it on a graphite mandrel, so you can make crucibles very easily this way. And I think we got some boron nitride from them. I think Mort was using it for a while, but I think that this was the introduction of the idea of using boron nitride for containing some of our materials. Well, to make things, to go a little faster here, I got sidetracked about this point. I finally got a metal system, and that changed my pattern of thinking a lot. I decided I was encouraged to try to grow MBE superconductors and set up a program to use E-beam evaporation to get refractory metals deposited. And this was looking promising, except that one afternoon I was not paying attention, and my technician turned on the machine and forgot to put the cooling water into the E-beam evaporator. And when that happens, it gets pretty hot. And when that happens, the brazing melts. And all of a sudden, he realized that he'd done the wrong thing. So he turned on the water at that point and filled up the bell jar. Well, maybe not totally full, but there was a lot of water in it. So that kind of ruined that experiment. I began campaigning trying to get a new bell jar, new MBE system, and was not very successful. So I had kind of a midlife crisis and decided that it was time to do something else. And my old friends at the physical electronics company invited me to come over and work with them. I think they did so because one of the things that I was doing at that time was using a low energy electron diffraction system to analyze the crystallinity of my films, but I was using it also as an Auger system. You can use a lead system to get the Auger spectrum. It's kind of crude and not very sensitive, but it worked. But it has the advantage that you can scan the electron beam back and forth, and so I could do some scanning. What time do you want me to, Jim? Where's Jim?
So, I don't know, another 3 or 4 minutes.
3 or 4 minutes, okay. We started late. I wasn't sure if you were going to make allowances. Anyway, I went to Phi, started trying to make MBE systems, and found that being a product manager was very different from being a scientist. It did get me a lot of interesting travel abroad. When the Ribert, well, I call it the Ribert meeting. Yeah, it was the Ribert meeting, sponsored meeting in Paris, came about. I went to that and went to New York and met Ed Badgett, the Ribert salesman there in New York, and he had us rigged up with a great big basket full of French food that we ate all the way across, and had a wonderful time getting over there. And it was my first visit to Paris. Very impressed, and I fell in love with the French coffee. And I mentioned this because there is a picture in the display that you'll see about this. The picture shows Al sitting at the table and me waving my hands around after having introduced him. Well, I was supposed to introduce him, but the fact of the matter was that with all that coffee, I couldn't get to sleep until something like 5 o'clock in the morning. And then when I did so, I didn't wake up. And my friends called me, where are you? You're supposed to be on. Well, so Al had to introduce himself. And as soon as he was finishing his talk, I strode up to the front and I said, "Are there any questions?" And I've never told that story. I've never admitted to Al that that's why it happened that way. But Al, I'm really sorry. That's the dumbest thing I ever did. Shortly after, or sometime after that, I decided that product management was not my forte. So I was fortunate to get the chance to go to Oregon State University and set up an MBE program there. The only drawback to that was that I found I had to do a lot of money raising to get things going. We wanted a new building and so on and so forth. So I had several trips to Salem to talk to the state legislature and the governor. In one of these meetings with a committee, I was telling them the beauties of what we were going to do, and all this detail about how wonderful this technique was for doing electronic things with crystals. And at the end of my spiel, this old legislator sitting in the back, he had his cowboy boots on and his string tie, and he just should have had a cigar in his mouth, but he didn't. Anyway, he was sitting there leaning back, and he said, "Tell me, Professor, just what is an electron?" And there was a twinkle in his eye, and I knew I had. So I started making some words. I'm not very good at expressing myself sometimes, and finally my dean tugged on my coat and told me it was time to sit down. Nevertheless, we got the money, and we did build a new building. But that brought up another part of my experience, was learning how things are done in a university. In a university, you have committees for everything. And so our building was a building designed by a committee. And we had a nice clean room up in the upper floor. Unfortunately, every time it rained, the rain poured into the clean room. Well, they finally got that fixed, but it's a lesson. The other thing that I found was that I got all sorts of advice from various other sources. For example, one old man came into my office, and he told me that he had a mountain of gallium that he and I could develop. And he meant it. I don't know what he actually had, but he had a mountain of gallium. Well, then we did have another prospect that sounded pretty good for a while. Okay, Jim's looking. I'm almost finished. One last anecdote here. We had a guy that had a program for building solar cells, and he wanted us to get involved in this. We were going to make a lot of money with solar cells. Unfortunately, it turned out that where he wanted to make the solars, where he wanted to put this plant, was where the Rajneeshis had built a settlement. The Rajneeshis were a cult of sort of a Hindu-related, not really, but they wore saffron robes and so on. The only problem with that was they ran into trouble because at the very end they tried to poison the water supply because the county commissioners were voting against them. So they ended on a very sad note, and of course we wanted to have nothing to do with putting arsenic into the area where these folks were. So that was a thing. So the end of it all is that shortly thereafter I decided to retire, and I've been very happy in retirement ever since. And I am blown away by what MBE is doing nowadays. I really envy you guys getting to work with all those nice toys out there. But in I guess the summary that I would really like to, the summary message is that this program MBE grew because there was a corresponding parallel growth of the electronic equipment industry. I mean the vacuum equipment industry. These tools, Auger spectroscopy, electron diffraction, so on and so forth, came along at exactly the right time. Timing is everything, and we had exactly the right timing, and that's why we're here today. Thank you.
Thank you, John. So we'll have, once the speakers in this session and then the three in the second session after the break, then we're going to have a round table and a discussion, so we'll have some opportunity. You can ask questions to all six of the first speakers here. The next speaker is Al Cho, most often regarded as the father of MBE. He was born in Beijing and came to the U.S. and received all three of his degrees in electrical engineering at the University of Illinois. He joined Bell Laboratories as a member of the technical staff and then was subsequently promoted to department head in 1984, director of the materials processing lab in 87, and director of the semiconductor research laboratory in 1990. Among Al's many research accomplishments, beyond certainly the development of MBE, were a very large number of device firsts. In the early days, he fabricated the first hyper-abrupt junction varactor, IMPAT mixers, field effect transistors, and artificial superlattice. But one thing these all had in common was that they were all majority carrier devices, and people really wanted optical devices. And I can remember visiting Bell Labs, and most of his colleagues at that time thought, MBE, good luck. If you hit it with a powerful enough laser, it'll get hot enough and it'll glow red. But any radiative recombination was a myth. And so Al then really did a lot of pioneering work on finding out some of the difficulties and background impurities and everything else that were causing serious degradation of the material, and ultimately they decided to develop the first MBE grown double heterojunction laser that operated at room temperature, and a story that I had something to do with, the first monolithic VCSEL on gallium arsenide. We were at a device research conference and ended up both in the same bar at some late evening, and Al was bemoaning the fact that they had this great result and it wasn't going to be presented. I said, what the hell's going on? That's what device research conference is for. So I was on the program committee, so I told Al, get your guy to the meeting. Tell him to go to Newark and fly to Boston in the morning. And I said the program committee won't meet until noon, but I called the program committee chair at 2 a.m. And told him we have to have another. Yeah, Bob Calowa. Right. And so the committee said, yes, we'll have this presentation. It'll be the very last thing at the meeting. And I tell you, it was amazing that the room still, the auditorium was more than filled. There were people standing there. Everybody stayed literally to the end of the conference to hear that VCSEL paper. So I guess I was forgiven for my rudeness of calling Calowa at 2 a.m. So Al has received many awards for his work on MBE, including the APS International Prize for New Materials, the IEEE Morris Liebman Award, the Gallium Arsenide Symposium Heinrich Welker Medal, ECS Solid State Science and Technology Medal, the AVS Geda Langmuir Award, and certainly probably the highlight, the National Medal of Science, was presented by Bill Clinton. Al is a member of both the National Academy of Science and the National Academy of Engineering, and he received the IEEE Medal of Honor Award recently. So, Al, it's a great privilege to introduce you.
Thank you very much, Jim, for the introduction. John, also, thank you for the nice introduction of Bell Labs' working environment. As you can see, we have fairly primitive equipment when we started there. But the important thing is, I want to stress that point. What makes a place is the people in there. What Bell Labs at that time is the people in Bell Labs. What makes Bell Labs? The culture and the way we approach things is what makes Bell Labs stand out above everybody else. Okay, now let me give my talk here. My talk today is how molecular beam epitaxy, MBE, was invented. Now I want to show this first view graph. You already saw, I already provided that in the poster there. And this is the first MBE conference, international conference, held in 1978. 1978 in Paris, France. Many of you probably wonder, why do we hold it in Paris? Why is it not in the United States? MBE was invented in the United States. The reason is because at that time, there was a big conglomerate investor called Instrument SA in France. And they bought Revere in 1976. After they bought the Revere, the president of Instrument SA, Dr. Gilbert Hyatt, came to me at Bell Labs, asked me, do you want to have an international MBE conference so that we can make the whole world knows that Revere is making MBE equipment? That's what the bottom line was. And he said, Revere will pay all the expenses. And I was at that time, I said, okay, go ahead, do it. So this is the meeting. You can see on the top picture there, John Arthur was on the podium there. I sit on the first chair there, Alcho. And the next one is Pierre Auger. In France, of course, they want to bring out the best of their scientists. Pierre Auger is the Auger, electron Auger, that we read in the textbook at that time. And he gave the first plenary talk, opened the international conference. And then the next two people is Boucher and Zhi-Yuan. They were actually the managers of Revere. Because they paid the bill, they got the chair on it. And here, Boucher getting more fat, but he's sitting there. At that time, he was younger. And now I want to start this talk about my outline. My outline is how was molecular beam epitaxy, MBE, invented. Then I will say, what was the road from basic research to production, which is a long, hard road for me to go through. And then finally, why is MBE the best technology for exploring new nano devices as well as for mass production? Now, as devices were getting smaller and smaller in the 1960s, and there's a demand for us to make small device as small as 500 angstroms to 1,000 angstroms. At that time, the liquid phase epitaxy had difficult to reproduce that thickness. So we need to have a new way to grow crystals. So MBE, John Arthur and I in the United States, and Bruce Joyce and Tom Foxon in England were studying adsorption, desorptions of atoms or molecules from solid surfaces in the 1960s. And we try to apply this knowledge to surface physics to grow thin films. I want to particularly thank John Arthur because I learned from him in regard how evaporate gallium arsenide for making thin films at that time when I finished school to Bell Labs. But I want to correct one thing. When I was hired to Bell Labs, at that time the department head was Carl Thurman. But Carl Thurman was kind of sick, and John Galt, the director, one level higher, was in charge for the department. And then I was hired by John Galt. And after John Galt hired me, then we have a new department head, was Jeffrey Garrett. I have Jeffrey Garrett for over a year, then Moore Panish promoted to become new department head of mine. So he was in charge of the department after that. So anyway, so after I learned how to evaporate gallium arsenide from John Arthur, as you know, as he mentioned before, everything made out of glass. Have good glass blowers. We put gallium arsenide even in glass capsules, try to evaporate from that thing. And then a lot of people ask me, what is this K cell you talk about here now, buy from the MBE equipment companies? K stands for Newton cell. Newton was a famous physicist, Martin Newton. And then in surface physics studies, we would like to have evaporation with the condensed phase equilibrium to its vapor in that enclosure. To do that, the cell, if you want to evaporate, the aperture of the cell, the diameter, had to be smaller than the mean free path of the vapor in the cell. So therefore, when you calculate, the aperture of the cell is so small, like a pinhole size. Now when I try to grow MBE with this pinhole size glass capsule to grow this layer, and the growth layer is very small growth rate, because growth rate is proportional to the aperture size for the growth. So I forget about Newton cell evaporation. I'm kind of more engineering brute force to take the aperture off, and there's no more Newton evaporation. I try to open the cell as large as I can. There's no more slits in there. So that's why, but the name remained, K cells. Now, John mentioned earlier about we use glass system. In fact, when I first joined Bell Laboratory, I had a fortune inherit Lester Germer's glass system. Lester Germer is the one, as you know, to demonstrate that was a wave. The electron is a wave. This very famous person, Davidson-Germer's experiment. So I felt there's a lot of problem. John had described how you have a glass system, how do you change it. You had to use gold O-rings every time you open it, only use once, a whole gold O-ring, how expensive that is. So I first tried to change the glass system into stainless steel. I want to point out here that I did this drawing here in June 28th, 1968. And then on the left-hand side is the glass chamber. On the right-hand side is the stainless steel cryo panels. And then we then sent in for make that chamber. Varian at that time is the manufacturing of chambers and some electrical equipment and so on. But they know nothing about what MBE is. They didn't even have the term of MBE at that time. So on the top here, you see the date, June 28th, I placed order, 1968. And then that chamber cost $2,035. And its delivering date, here you couldn't see, I made it big and in red, 2 to 6 weeks shipping after receipt of the order. And the engineer at that time signed over here, his name is the marketing engineer, Ed Graney. And then I want to show you the chamber arrangement. Here is from top, look down the chamber. This is the stainless steel chamber here now. And then the liquid nitrogen feed shroud in the center, and the diffusion cells. And of course, the diffusion cells and all those, we had to make it ourselves. No one else. You were not so spoiled. Just place the order, the system delivered with cells, guns, everything is in there. Just push button, you grow the materials. But those days, we had to make everything. We had to wind the diffusion cells, and then here I bought a high energy electron diffraction gun, and then placed over here, and then diffracted over here. But when I first made the design, I over-designed. I used a 50 keV electron gun. I thought I could get better diffractions and look at better effect on the surface. But I didn't realize 50 keV produced soft X-rays. So I had to put all the glasses, lead glass, in the diffraction screen. It's a nuisance. So from then on, then the next generation of MBE diffraction guns lower down to 5K, 10K. And of course, I'll show you why the difference of 5K, 10K is there's a difference in the diffraction of higher energy ones. Higher energy ones, the able sphere, the diameter is smaller. So when you have the reciprocal rods there, they can look at higher orders of the reciprocal rods. So you can see more so than the 10 to 5 keV, you only intersect the first order. So anyway, here shows at that time, in 1968, I was able to buy a commercially available EAI quadruple mass spectrometer and from Varian. And I want to show you here is after the system delivered in 1968. I just want to show you, I put on this, I don't wear a suit and tie in growing MBE crystals. I put on a suit and tie just for the picture's purpose. And here shows the chamber I just ordered, and after 5 weeks, 6 weeks, I got delivered. And then, of course, there's no manipulator, sample manipulator. And in the center here, we try to build the sample holders. After we build the sample holders, then we put it on top here and then make the MBE system. Oh, okay. Now, let's get serious here. How was molecular being invented? How do you invent something? To me, is A plus B gets C. When you applied the knowledge of 2 different technologies, and then you create a third technology, that's a new thing. You invent a new thing. So for me, after I finished my master's degree in Illinois, I got so tired of working and then studying at the same time. I told my advisor, I said, I need to take a break. And he said, well, what do you want to do? I said, well, I just want to have a work. I haven't seen Boston, East Coast of the United States yet. After I landed in the middle of United States, University of Illinois, I haven't seen East Coast or West Coast. So it's all just, to me, Illinois is just a cornfield. Where's everything? So he said, I gave you a job. I know friends in Boston. So I got a job at the high voltage engineering subsidiary called Ion Physics Corporation. And over there is through the, at that time in 1960, we got behind of the Sputnik in Russia. So John Kennedy was the president. Everything you put a proposal with the word rocket in there, you got contracts, you got money. So everybody is doing rockets. And what we're doing is called ion rocket. The ion beam rocket is, of course, not shooting from Earth to orbit. It's this very efficient beams that controls the altitude turnings of the station after you shoot up there. Okay, so with that ion propulsion work, I learned I learned the temperature controllers with the electronic negative feedback systems. You know, like John said earlier, when we get Bell Labs there, it's very primitive equipment. When I try to evaporate a cell, we have a glass tube cell, hand wind a heater, and then with a variac over here. So heater, higher temperature, lower temperature, just by turning the variac. So we have to be more sophisticated. And then I learned there's something that called negative feedback. With the thermocouple, negative feedback system could control the real temperatures. And then we have liquid nitrogen cool shroud and the heat shielding for the diffusion cells. These rocket cesium ion beams with the diffusion cell coming out, this temperature had to be very well controlled. And how do you control the temperature? Besides the negative feedback systems, the cells are surrounded by heat shielding, tantalum foil heat shield. And then the low log sample exchange. Well, with surface physics, what we learn? We learn atomic absorption, desorptions, mass spectrometries, high energy, low energy electron diffractions, ultra high vacuums, and clean surface. Add these 2 together. We try to grow crystals, now called molecular beam epitaxy. Now, This just shows you some of the reports. In 1961, I joined Ion Physics Corporation, and of course, this report is for NASA, National Aeronautical Space Administration. Yes, sorry. We also call it NASA. Okay. So in there, the title we have here, I just enlarged it bigger, says Ion Rocket Engine System for Altitude Control and Space Keeping. And after 1 year, as I mentioned, I went to East Coast. I saw Boston, how nice it is, and but I haven't seen West Coast. My mother and father all migrated to California. I haven't even seen them. So my professor, Chuck Hendrick, is very good. He just wrote a letter, and then I got a job at TRW, Redondo Beach. That's the Space Technology Laboratory, TRW. And over there, continue, as I mentioned, everybody worked on rockets. This is continue to do the ion emitter rockets for space stations. And I joined there in 1962 and worked through the report, again, for NASA report. By 1964, we wrote this report, authored by me and Hayward Shelton. I want to particularly acknowledge Hayward Shelton taught me everything about how to absorption, desorption studies, because he was MIT PhD from Nottingham. Nottingham is a world-famous surface physicist. And he was Nottingham's last student. And there were Nottingham symposiums every year on surface physics. So Hayward Shelton taught me everything about surface physics. Then in that report, I just want to show you this picture. This is in the report about cesium ion beam source studied from 1962 to 1964. Notice here, these cesium diffusion cells that heat shield by tantalum foil to keep the temperature uniform. And then look at this. After I joined Bell Lab, tried to improve the technology of diffusions and then maybe use it for grow crystals, and I designed from the glass capsule to the tandem heat shield diffusion cells. Even today, MBE, you can see that cells still similar to the one I had in the first NASA report. And here just shows the diffusion cell in operation in the liquid nitrogen cooled shroud. Now, turn back time a little bit again. In the study, I learned with Hayward Shelton, and we had to study adsorption, desorption of atoms on solid surfaces for the cesium ion sources. And then the work of 62 to 64, we found it published in Journal Applied Physics in 1966. In that paper, this is direct reproduction of the paper, figure number 1. We have diffusion cells here and shutters and molecular beams coming up there through the shutters and then hitting on the substrate. The desorption from the substrate is ionized going to a quadruple mass spectrometer. This is in 1962. As you know, there is no commercially available quadruple mass spectrometer in 1962. I had to study and read in German, a German thesis by Kahn, try to understand how quadruple mass spectrometer works. We built ourselves this quadruple mass spectrometer with electronics, and then we do the measurement. And of course, 5 years later, like 1967, this become commercially available. In that, John Arthur alluded earlier, when you open, close the shutter, you see the exponential curve on and off. And then by looking at the lifetime of that, you plot the Arrhenius plot. You get the activation energy of this molecules on the surface. I went back finally. My professor came to TRW, told me in 1965, Al Cho, if you don't come back to Illinois, you're fired. You're no longer can be a PhD candidate anymore. I said, yes, sir. In 1965, I dropped immediately everything. I was going to be a beach boy in Redondo Beach, but now the whole dream shattered. And then in February '65, I hopped on the car, drove to the snowy Middle West Illinois, and checked in the dormitory there. And of course, 5 years gone, from 61 to 65, everything changed. At that time, when I left there, there's no qualifying exam for PhDs. When I go back there, there's a qualifying exam. And worse yet, electronics changing from vacuum tubes to solid-state electronics. I had no idea what semiconductor is. I had a qualifying exam, I fall flat. But my professor is so nice. I owe all my success by Professor C.D. Hendricks. He said, don't worry, first semester, just sit in the class, learn semiconductor, and then you can take the qualifying exam. I never worked so hard in my life. Day and night, weekend, I don't care. There's no more anything. Just study. You remember when you go to class, you're doing good. That you do the chapter in the back, odd numbers or even numbers. I go from number one to number last. Every questions in each book, I study. I made it. So I passed the qualifying exam. There were 31 person took, 11 people passed, and I was number 2. So I was doing well. So in that thesis I finally wrote, I was, of course, had an advantage. I was doing that work, surface physics work in TRW. I just extend that as my thesis. So in my thesis, I define the condensations or sticking coefficient equal to S. Is S equal to 1 minus A over B. A is when you open the shutter, abrupt change up to A, and then the exponential equilibrium to the value of B. Look at the two extremes here. If A equal to B, then that sticking coefficient is 1 minus 1, 0. There's no atom absorbed on the surface. The other extreme, if A equal to 0, then the sticking coefficient S is equal to unity, 1. That means every atom you hit on the surface sticks. You ground there. Therefore, and of course, in between, there's can be fractional of the thing absorbed in 0.2, 0.5, so. Now, with this, John Arthur make the most important study of the surface physics in absorption, desorption work. Notice here that when this showing here the arsenic atom coming out of the surface when you open the shutter, as a function of time, with that curve here. Abrupt change go up there. That means A is not 0. Okay, all the arsenic atom didn't stick on the surface, and on and off he shuttered. The important thing here, when you get it here, you turn on the gallium beam on the surface. You have a gallium-covered gallium arsenide surface. Now, when you open the shutter, look at here. Exponential curve start from the beginning. There's no abrupt increase there. That means A equals 0. Unity sticking coefficient. So that's what makes us know. You want to grow gallium arsenide? If you can plaster the surface with arsenic, doesn't matter. They're just bouncing out of the first surface. So as long as you have enough arsenic on the surface, gallium on the surface, you grow gallium arsenide. And Tom Foxon and Bruce Joyce did also the experiment that he's plotting here is sticking coefficient of arsenic as a function of gallium beam arrival rate. Again, when the gallium beam arrives with more, the sticking coefficient of arsenic increases more. That was published in 1977. I want to show you a little bit about, I actually bought the heat system, very, very expensive. Here is the 1968 when I first get to Bell Lab. They give you an empty room. That's so exciting in Bell Labs. After you come out of school, you go in, check in Bell Labs, empty room, a table, a paper pad and pencil. Start. Sky's the limit. And you go where you want to go. And then, of course, the other thing I was lucky have John Arthur sort of coaching me. This is good. What is it now? We grow gallium arsenide. So I had an idea. Of course, when we try to grow things that he was telling you earlier, the first one we tried to grow diamond for that, because on the other hand, when we try to evaporate graphite, graphite come out as chained, C7. When it hit on the surface here, still C7. Therefore, you grow a graphite film on there. You don't grow diamond. So anyway, I just in Bell Labs here, you can have a first dose of money that what you want to do your experiment, you buy equipment. So after I spent $3,000, whatever, made the chamber, I want to have heat gun. But the heat gun is very expensive. 50 keV gun I ordered, $41,000. Oh, that was absolutely, it was like unbelievable expensive. Okay, where compared with the chamber, I said down here, bottom here, is only $2,035 where the gun is mounted in there. So anyway, I bought it. John Gall was good enough. He hired me. He figured, well, give this guy a chance, see what he can do. Even $41,000. He signed it. And then, but you see, this gun gave me a really important road how to grow films. It was a great surprise to observe the surface structure changes as a function of substrate temperature and the relative fluxes of arsenic and gallium incident on the gallium arsenide surface. I interpret the conversion of surface structures is due to surface composition changes. And later I use that surface composition changes plot the surface phase diagram. But when I first presented this reconstruction of surface structures in 1970, I met tremendous oppositions of resistance from the surface physics community. And at that time, the surface physics, all this community considered this surface structure is due to the impurity surface sitting on the clean surface. For instance, oxygen on nickel 100 surface produce a center 2x2 surface structure, published by Al McRae, very famous surface physicist in Bell Labs, in Surface Science in 1964. Now, surface structure, I was so excited that I found gallium stabilized surface structure, square 19, arsenic stabilized surface structure, 2x2, on the bar 1 gallium arsenide surface. But I forgot to ask myself, after all this work, when you get the result, anybody cares? Well, the answer is maybe only 3 people care in the whole world. Well, anyway, I did publish that result in Journal of Applied Physics coming out in 1970. Why did you like it? No one cared because the industry only used 001 gallium arsenide substrates. They don't care about bar one surface. So from then on, I immediately changed to study on the 001 surface. And of course, I mentioned earlier a little bit is when I look at the square 9, that was on the 111 surface. On the 001 surface, I saw center 8x2, center 2x8 surface when I use a 50 keV gun. If I lower the gun to 10 to 5 keV, I see 2x, 4x structures, which you all see today. That is arsenic to gallium stabilized surface structure. Now, in the same year, 1971, I also reported the diffraction pattern on the right-hand side, and then the corresponding surface structure. Look at the carbon replica on the left-hand side. When you have a gallium arsenide surface, when you clean with bromine methanol, and then you think it's very clean, you put in the MBE system, heat it up, dissolve the oxide. What happened? You look at diffraction patterns, spotty diffractions. The reason is because after heated up, they have microfaceting. The surface has little tiny hills and valleys. The electron beam, diffraction beam, coming on the surface with a grazing angle, had to penetrate through the protuberances on the surface. Three-dimensional Lowry condition has to be satisfied. Three-dimensional Lowry condition gives you spot diffraction in the reciprocal space. Now, when I grow with MBE on the surface, it forming larger, smoother areas. And you see here, the second one, the diffraction pattern getting a little bit more streaky. Okay? And then finally it gets so smooth, atomically smooth, the diffraction pattern becomes streaky pattern. Why? Because two-dimensional Lowry conditions are reciprocal rods. The avosphere intersect the reciprocal rods at the 0th point here are lines. Furthermore, when we get so smooth, you see the fractional 1/2 order showing in the 110 azimuthal direction. That shows the atom in the 110 azimuthal are 2 times larger than the bulk crystal in real space. So with that, I find out if you get different arsenic to gallium ratio, different substrate temperatures, I therefore plot the arsenic to gallium ratio in the vertical scale and 1,000 over degree K on the horizontal scale. I plot their arsenic stabilized surface structure and then gallium stabilized surface structure on the left-hand corner. As you all know, today, when we grow shiny, smooth surface, we always want to try to grow an arsenic stabilized surface structure. Why? It's just like John Arthur earlier showed, that any additional arsenic atom, they just bounce off anyway. Doesn't matter. So as long as you have enough arsenic atom on the surface, you grow shiny gallium arsenide surface. But too much gallium on the surface, what happens? You got gallium beads on the surface. You got a hazy surface, finished. Okay? So therefore, we always grow on the arsenic stabilized surface structure. The term molecular beam epitaxy, thank you for more Panish, that was the first time we used in the talk, the symposium, international symposium on gallium arsenide and related compounds held in Aachen, Germany. More presented the talk, but I stayed back in the United States, keep on working. You know, he was my first, he was my new department head, as I said. Jeffrey Garrett moved out, and then Moore Pennish become my new department head. And then here is the paper. The paper says, the title says, molecular beam epitaxy of gallium arsenide, aluminum gallium arsenide, and gallium phosphide. Author is Cho, Pennish, and Hayashi. So that was the first time MBE, the term, was used. Superlattices. The proposal by Leo Isaki and Ray Zhu that on the negative differential conductivity in superlattices open a new dimension, and that would not be possible in bulk semiconductors now appear to become possible in superlattice structures. They published in IBM Journal Research and Development in 1970. I saw that paper. I immediately demonstrate MBE superlattice structures. Here in 1971, Applied Physics Letter, I showed with MBE, easy to make superlattice structures. As you know, superlattice structures depend on what compound you make the superlattice structures. These band alignment are different. You can align in type 1, type 2, type 3 different alignments. One is you can have electron holes in the low band gap materials layer, or the electron in the low band gap material, the hole in the high band gap material. or they're mixing, depending on you're growing gallium arsenide, aluminum gallium arsenide superlighted structures, or Indian gallium arsenide, gallium and timonite arsenide, depending on what compound you want to use. Here now, with time limit, I want to continue to introduce you MBE grows of single crystal metal. We grow single crystal aluminum on gallium arsenide. And then with that, we made micro Schottky diodes, which has extremely low noise temperature. At that time, this single crystal Schottky diode was applied for application in radio astronomy at that time. MBE contribution to the basic research is also quite extensive. For instance, the growth of high purity gallium semiconductor layers, Horst-Romer, then Cui discovered fractional quantum Hall effect, and then the growth of superstructures of metal layers, Furt and Grunberg discovered the giant magnetoresistance. Nobel Prizes were awarded for both of these discoveries. In 1970, the start of MBE device applications. I know that only after we could demonstrate new devices and new applications, we can change the world. But the first demonstration that I tried to show is to grow a double heterogeneous injection laser, because Moore-Panish and Hayashi just demonstrated with liquid phase epitaxy world first semiconductor laser lasing room temperature CW. I want to do that. But when I try to do that, not even laser, didn't have any light coming out of there. Fall on my face. Go back to the drawing board. Now, Hayashi was constantly monitoring my layers luminescence, photonic measurements, that he finds that their days are good, their days not good. He said, what did you do? And I said, I didn't do anything, I had to grow the same way. But then I finally looked at all my data. I analyzed, hey, during summertime, my luminescence of aluminum gallium arsenide is horrible. During wintertime, are pretty good. Why? Because in New Jersey, summertime humidity very high. Whenever I open the system to change my substrate, the whole chamber is water vapor condensed in there. And I couldn't grow reactive aluminum gallium arsenide. So I therefore said, from the earlier days of low Lux studies in the ion propulsion work, I'm going to put a low Lux in there. So with the help of Paul Lucier, here, Varian, early days, all my chambers were made by Varian. And then Paul Lucier especially helped me a lot in designing the liquid nitrogen cooled shroud here. At that time, I didn't know they had a skill can wrap around a diffusion cell with liquid nitrogen. They can weld so well. But Paul Lucier knows, he's from Varian. And so we have the liquid nitrogen cooled shroud completely surrounding the growth chamber, diffusion cells. And then here's the big bellow. Well, what I did is I had that sample mounted in the center here, that rod here. We first pull out this to the end. The gate valve is closed. We mount a new sample in there. After the pumping with auxiliary ion pump over here, then when we pump down to 10 to the minus 7 or whatever, and then we open the gate valve, inserting this big bellow rod. It's really very ugly, to send it into the center there for the growth. The problem is, while you're growing, you cannot close the gate valve because the big bellow, this rod, is in the way. So we had to grow with that bellow exposed to the growth chamber. As you know, bellow had a lot of surface area, absorb all the contaminated air and water. And even pump down 10 to 9 to 7 was better than open up to air every time you open, changing the sample. But it's improved, but not ideal. So we go on to the next generation. First of all, I want to show you. I actually had the system pictures here. The top part of here is the 1970 MBE chambers. By the 1975, we're putting this bellow things here. This is the red here is auxiliary pumping here. but you can see this is half moon looking. Why is half moon? Because the bellow cannot go that far. We had to cut down the round chamber into half moon so that the bellow can reach to the center for the growth. We need to have a better design. So I would keep on trying to see how we can absolutely isolate the growth chamber from the low lock. There was a very good engineer. His name is Buisson in Revere. And he helped me. He introduced this so-called magnetic coupled transfer rod. So what I can do now, I mount the sample on this magnetic transfer rod, and then open the gate valve, inserting the sample into this manipulator here on the molybdenum block. Rotate, clock, put on this holder here. And then I retract this rod back into the low lock system, close the gate valve. So now I have completely isolation of the growth chamber and the low lock when we mount the new sample in here. From there on, of course, I have the best vacuum for the growth. I just want to show you a little bit. Jim Harris earlier alluded a little bit how I first tried to do the majority carrier device. Why? After I first show you, I fall on my face. I tried to follow more panish liquid phase epitaxy, grow a laser. I couldn't make a laser. I have very good collaborators in Bell Labs. I told you earlier, what makes a place is the people in the place. In Bell Labs, they not only have experts in every field, they have 5 experts in every field. So I can always find a good collaborator which I can talk to, I can work with. If you have even have an expert, if he has very bad personality, you don't want to work with him, you can work with the next guy. So I was so lucky to work in the place. I have so many talented people. Now, I have Franz Reinhardt across the hall from me. Franz Reinhardt said, oh, well, don't get too depressed when you couldn't make that laser. It's not the end of the world. You try to demonstrate what MBE can do, LPE cannot do. What? He said, well, MBE can grow doping profiles any way you want to dope. You can dope exponential curve doping profile. You can grow low, high, low, abruptly changing within monolayers, changing the doping profile. No one other crystal growth technology can do. And so you couldn't make the laser to lace, and let's do something with majority carrier devices, just electrons. So what I did is first, so in 1974, that demonstrated the first MBE microwave device called the gallium arsenide voltage varactor that have a doping profile in the voltage varactor is exponentially increased. What that does is the capacitance changes linearly with bias voltage. Like very important for all your TV tunings or all these applications. Now in that works, the second one is the first MBE impact diode. The impact diode is, at that time, dying to have some doping profiles called low, high, low impact diodes that no one can do. MBE demonstrated. So that was actually used in the first test of microwave tubes in Washington. But then after we did that, the changing from microwave transmission to optical transmission. So therefore we went on to continue to do laser work rather than microwave transmission. So then I mentioned we introduced low lock exchange in 75, and then very importantly, by 1976, I demonstrated the first MBE double hydrogen injection laser lasing CW at room temperature. If you can do that, you almost practically can do any other devices because it's most critical to make that CW room temperature lasers. And then continue to develop MBE. By 1980, we go into long wavelengths with Norman Chen in my lab. They're growing Indian compound materials. And then we need to have more uniform growth. With Norman Chen was in my lab, we demonstrate the first rotating MBE substrate holders to get more uniform growth. And then we'll continue to make the 1.55 micron aluminum gallium arsenide double hydrogen injection lasers, these room temperature. I just want to show you this view graph. This is the milestone that demonstrated MBE can make room temperature CW laser. That was published in the Applied Physics Letter in 1976. The road from basic research to production, it is a long road. I just want you to have some feeling for it. For crystal growers like us, we first grow a layer, we look at the surface morphology, take a picture with a Novarski camera, and then we publish paper. And then next difficulty is the crystallinity of the structure. Are you polyscrystalline? Are you a single crystal? Is there a defect in there? And then next level up is transport properties. After you grow a crystal, you measure mobilities. The mobility can be terrible because of traps and all the other things in there. You had to grow very high quality materials, purity, to grow high mobility devices. And of course, next level higher is look at the photoluminescence. Now you look at the minority carrier device. It's harder yet. And then you can make PN junctions. Hard PN junctions is not easy. Is you have to have interface very smooth and doping profile, abrupt changes to get good PN junctions. After you did all that, I can start make devices. So you make a device, you can publish a paper. But then, the important thing is, you can't just make a device which lasts 10 minutes, get the data and publish a paper. You gotta make a device which will last 10 years and 20 years to be any useful. So even worse yet, after I finally make it to have a high reliability devices, and then the manager comes here and says, is it cost effective? You cannot make a laser $5,000 and then try to make it people using the CD players who want to pay $5,000 for a CD player lasers, right? So I find in order to reduce the cost, we need large volume production. But it is extremely difficult to convince MBE equipment companies to make the first production MBE system. I remember clearly, in the 1980s, I went to Revere and here, I help you make the first MBE, International MBE conference, and then I was working very closely with Mr. Buisson, and then here Boucher was there also, and I tried to convince the president of Revere to make a MBE production system. He said, okay. What are you going to use it for? I said, lasers. And they said, how many lasers you need a year? I tried to stretch my memory. 1 million, 2 million. And then he said, well, what other thing you want? I said, microwave devices. How many you want to make? At that time, we don't have cell phone yet. I said, another 1 million, another 2 million. And then he make an envelope calculation. You only need one production MBE system for the whole world. That was the end of our conversation. It was, forget it. I spent all that money making the system. I can only make one production system for the whole world. I'm not going to make it. So I had to use tremendous pressure, convincing them, saying, if you have the equipment, people will find use for that. You'll get more applications. More people are going to buy it. And then, of course, with that conversation, and then I went back to Dr. Gilbert Hyatt, who was the owner of Revere, and I said, we can develop the next generation. You have to have a little bit of vision what the future is going to be. So with the pressure from the owner, from the other things, everything, finally, Revere launched the world's first MBE production system in 1988. Here's one of the systems. You can see why he didn't want to do it if you only sell one. spend all that money, put the software in there, automations in there, you put a wafer in there, push a button, you come out the other side, the gross layer, okay? You can see that you have platinum on there, mounting many wafers on there. Put in the cassette, you one by one transfer into the gross chamber, okay? Now, this MBE production system, very uniform. The uniformity of the thickness is 0.5% across the wafer. And then very stable. The most important I want to show you is that very high uptime, 94% uptime. The run is you can have 6 to 9 months time of running before you open the MBE system. It runs 7 days a week, 24 hours a day. That continuous running, you can run 6 to 9 months without opening the system. And then large platinum, these days you can have 25 3-inch wafer mounting on each platinum. And then you can mount 7 6-inch gallium arsenide wafers on each platinum. Furthermore, the changing time from platinum to platinum it only takes 2 minutes. Now, this is extremely important. For, as you know, our competitor, MOCVD, is constantly eating our lunch there, that the changing of platinum to platinum in MOCVD is a lot longer. And of course, there are many other advantages of MBE versus MOCVD that, of course, they have also their advantage over MBE also is another topic that we can talk about. Here, I just want to show you, a lot of people think MBE is not for mass production. But the micro device, RFMD, and now IQE, that Amy is here, that they produce 500 million chips per year. As you know, in the United States, only 200 million people. Now, we supply across the world of this MBE-grown gallium arsenide amplifiers, RF switchings. Every cell phone has 4 RF switchings in there. They're all made by MBE. Now I want to move on to give you a little bit a talk about the future. And in semiconductor optical sources, here plotting the wavelengths, 1 meter to 0.1 micrometer. The green area shows electronic devices can cover that frequency. The yellow part shows the semiconductor lasers can cover that range. And then there's a blue area in the middle, big gap. The mid-infrared range from that 300 microns to 3 microns range, God didn't give us the material, we'll have that band gap to give us that wavelength. And of course, you saw in here middle, 10 terahertz is right here. We talk about terahertz, future of electronics. It's also in this range. Why this mid-infrared range is important? Because most of molecular vibrational energy, that frequency, is in that mid-infrared. So, in Bell Labs, we invented the quantum cascade laser, which is a completely new laser. It only uses one kind of carrier, electrons, no holes, just electrons that can, in the inter-subband transition, that give out light. In 1994, we published the first quantum cascade laser in that Science magazine. Okay, here is the team we have. It's truly international team. Here, the first one on the left-hand side is Federico Capasso. Is my longtime collaborator. And then me in the second one in white shirt. And the third one, Al Hutchinson, is the lab assistant of Federico Capasso. And then Debbie Sifko is my lab assistant in MBE crystallograph. Then these two are the postdocs. The Jerome Face is the postdoc from Switzerland. And then Carlos Sakura is the postdoc from Italy. So it's in Bell Lab. It's attract the world's best people. Doesn't matter what race, what gender, where you come from, what your habit of doing research, as long as you're good. I think that's what makes Bell Labs Bell Labs. Now, quantum cascade laser application can be used for industrial process controls, the medical diagnostic for ulcers, liver disease, kidney malfunctions, asthmas, and then for domestic security, military detecting explosive, narcotic, biological warfares, and terahertz devices. And then it's now manufacturing. You can buy the quantum cascade laser equipment. And then in California, this company called that Paranetica, and you can buy quantum cascade laser equipment, 3 watt output, 20 watts output CW, room temperature. So in summary, MBE is broadly used today for devices, nano multi-layer structure productions, and radically new devices including quantum cascade lasers, high-speed transistors, microwave devices, microjunction solar cells, laser diodes, and detectors. Most of today's semiconductor lasers using compact disc players, CDs, ROMs, are all manufactured by MBE materials. MBE is also used in fabricating the RF switches and power amplifiers used in every day of our mobile phone today. That Russia gave us the MBE, the first international nanotechnology prize, the Rus Nano Prize, in 2009. I want to thank you, all my fellow MBE workers, that I was so fortunate to work with many outstanding scientists and engineers. Many of you are here today. And when I think about what in my career, what the most important aspect of all, that was working with a team of most capable people and having mutual trust and mutual respect. That is the most important for our success. Thank you very much.
Great talk. So the next speaker is Tom Foxon, who will provide a perspective on the development of MBE in the UK and Europe. Tom earned his BS degree in physics at King's College in London and PhD in materials science at Battersea College, London University. He first served as a postdoctoral fellow at the University of Surrey and then went to the University of Alberta and then joined the Phillips Research Laboratory in Red Hill. Tom developed one of the key things is modulation beam mass spectrometry that became one of the key techniques for the basic study of the chemistry on the MBE growth process. This provided a foundation for the growth of extraordinarily pure material and ultra-high mobility 2D electron gas structures where he and collaborators observed the quantized conduction and point contacts, measurement of charge of the quasi-particles in the fractional quantum Hall effect. As a result of his pioneering work on these ultra-high mobility structures, he was both a professor of physics and astronomy at the University of Nottingham, but also a visiting professor of physics at the Technical University of Eindhoven, where he could continue his collaboration with the Phillips Eindhoven group. And I've forgotten Hank, the guy that did a lot of the 2D
Hank
gas.
Hank Van Houten.
Yeah. So over the years, Tom has worked on a great variety of different materials. He's a fellow of the Royal Society and the recipient of the first Al Cho MBE Award, which I had the great distinction of presenting. I was the chair of the MBE committee at that time, and it was in Edinburgh, and so those of you who were there remember I wore my kilt for the first time. It returned to Scotland to its original home. So with that, Tom.
Thank you. Thank you, Jim. Okay, so I want to speak about the history really of MBE at MRL as they were, Mullard Research Laboratories. In the beginning, it later became PRL, Phillips Research Laboratories. And then finally, I moved with my colleague, as we'll see, to Nottingham in around about 1991, and I'll explain why. It's a salutary lesson, I think. Okay, so the project started again when I met Bruce Joyce and Jim Neve, who'd moved to MRL shortly before I came there. They'd previously been working at Plessey. And it actually started, the project started, as we'll see in a moment, in February 1970. The reason was nothing to do with growing layers. The reason was that Mullard's had a problem with their gun diodes. And the idea of this project was simply to use this modulated beam mass spectrometry to study gallium arsenide and to see what was going wrong with their production process. Life didn't work out quite that way, but we'll see why in a minute. Our first publications were a little bit later than those from Bell in about 1973, and that work continued until we moved, I must say not voluntarily, to Nottingham to do the work there. Okay, before getting on to what happened at Mullard's, there was work earlier at Plessey by Bruce and his collaborator Bob Bradley, where they were growing silicon from silane in a UHV system, fully developed UH system with diffusion pumps, something you wouldn't see on an MBE system these days, but they're actually very efficient for pumping gases. And in fact, you can handle with a diffusion pump things that you can't handle as easily with other pumping systems. The beam was formed and then impinged here on the heated target. So this was, from my point of view, a very early example of growth from a molecular beam to produce a semiconductor film. So here you can see silicon islands grown on the silicon substrate. They're clearly epitaxial, as you can see from this picture. So this is long before we were working at Mullard's. Well, coming back to Mullard's, the project, as you'll see, was conceived in October 1969. And for a curious reason, you see only my name there. The reason is that at Mullard's at that time, if you had a project, which Bruce did, you couldn't have a second project. So curiously, Bruce's name doesn't appear here, but it really was a collaboration between all of us. You can see the budget cost for it, £4,000, wow, and £12,000 in a later year. And the probability of getting a contract for this, 0. But, okay, so this was the first system that we put together. Jim Neve here, everybody should remember Jim's name. He was actually vital to all of this work. He was the guy who had the experience with ultra-high vacuum equipment. And Jim's contribution cannot be underestimated. So you see in this first system we have the molecular beam source. I'll show you in a moment. It was modulated by an in situ rotating motor, fairly unique. Ferranti made this UHV motor, which you could buy. And that allowed the molecular beam to impinge on the substrate, and the desorbed beam could also be modulated by a second motor. And the mass spectrometer was situated here in a liquid nitrogen cooled region, so that it was a first pass through there, and anything that went through was frozen on the on there. And we had a second molecular beam source here to just look at what comes from the source itself. Shortly after that, this system was modified because of the work that was going on at both at Bell and IBM. And in fact, we used the electron gun from the Auger system cylindrical mirror analyzer here to provide a read pattern on the surface, and introduced a vacuum interlock, even at that very early stage. But other than that, it was essentially the same system. Okay, what did it look like? A bit of a mess, really. But you can see the chamber itself, a huge iron pump here. Mullard's actually made their own UXV materials. And this Mullard iron pump, 500 liters per second, still exists somewhere at Nottingham. I haven't found it recently, but it still is there. And you can see the pumping, the two absorption pumps. It was computer controlled. There was a guy called Boudry who walked in from Australia, and he was a really good electrical engineer. And he put together a system of a computer interface here in the very early days. The computer had 4K of memory. Okay? And that computer managed to run the whole MBE system. It's amazing. But there you go. Okay, so looking at it in a bit more detail, you can see the various components, the Auger system here. This is the version 2 with the read screen here. The manipulator, sample manipulator on the top. We had 4 Knudsen cells with their independent shutters, and the mass spectrometer. That still exists in my lab in Nottingham, and it still works after all of this time, amazingly. The cells were homemade, as Al said. Just look at the dimension here, 1 millimeter. These were not exactly large cells. They were nevertheless true Knudsen cells. You can see that the internal surface area here is very large compared with the size of the aperture. That's a second requirement for a Knudsen cell. And what we paid attention to was making sure we measured the temperature accurately. So there's the thermocouple welded to a plate here, so it really does measure accurately the substrate, the source temperature. Okay, things moved on. Slightly sorry, beg your pardon. Go back one. So slightly larger cells here with larger capacity, but again still a true Knudsen cell rather than the modern cells that we use it, which really ought to be called Langmuir cells because it's Langmuir evaporation, but it never caught on. Okay, so all of that led to the development of the models for growth of gallium arsenide. Essentially, this one reproduced what John Arthur had done earlier, showing that the sticking coefficient of arsenic was 1. It's more complicated with the tetramer, and it's a much more elaborate surface reaction here. It's a second order reaction. Bruce was in his element with this. He was a chemist by training. He was only ever interested in MBE as a route to understanding chemistry. That was his forte. We went on to look at mixed group 3 elements and mixed group 5 elements. So we covered pretty well the range of 3 5s. One of the most important things that came out of the work at Mars was this observation here. Not my work, that of Jeff Harris and Bruce Joyce. Other people had previously seen oscillations in the read. In fact, John here describes it beautifully in one of his review papers. The key thing here, however, what Jeff realized was that the frequency of these oscillations corresponded exactly to the deposition rate in monolayers per second, which proved that the reed oscillation was associated with growing monolayers of material. This picture here, which appears in many, many papers, was actually drawn up not for scientific reasons. It was drawn up to explain to the management how reed oscillations work. So this, and in fact, this still exists in my office in Nottingham. Anybody who wants to see the original can come to Nottingham and see it. Yeah. It's there, in colour. Yeah, the published ones are in black and white, of course. Yeah, but the colour version is in my office. You're welcome to see it. Okay, so then we developed, of course, again with the help of Jim Need, the various cells, including this first arsenic cracker, which was developed very early on with Jim's expertise, and of course cells for doping and cells for growing, seriously growing material. This is the first homemade system for real film growth at Nottingham. Colin Wood was involved at this stage, and John Roberts, who subsequently deserted to grow by MOVPE. So he went to Sheffield to do that work. This was the first commercial system we achieved. A very young Jeff Harris here, operating that system. It actually was used to supply 35 gigahertz mixer diodes to Marlons at Hazel Grove in as early as 1982. They were sold on the market. So this may represent one of the first commercial uses of MBE for actual devices that were sold to the public. And it's little known, I think, outside this one. Then in 1985, we got the second commercial system. This is a Varian Gen 2 with this curious system for introducing samples here with an Auger system built into it. And that operated from, the first layer was grown, as you can see here, in January 1985. In the UK, we don't have this curious example of putting the month first. So things are slightly different. And it grew a total of 950 layers, and it ran until they kicked me out in 1991. So it was a very successful piece of kit. We were involved in lots of races of one sort or another. The race really that was really interesting was to provide the highest mobility two-dimensional electron gas possible. And various people contributed. It was a truly international effort. There were breakthroughs in Germany, in Japan, and of course in the USA, as well as in the UK. Our best ever sample here, G635, grown in 1989, had an extrapolated mobility of 1.2 by 10 to the 7. That's cheating, isn't it? It really is. But in fact, Lauren Pfeiffer, whom I'm grateful for this slide, was the first person to actually achieve 10 to the 7 at 1 Kelvin. Nevertheless, we got pretty close. Maybe we got the silver medal or something, I don't know. And again, there was a great contest. This was a UK contest, actually, looking at this business of quantized conduction in point contacts. And contrary to what most people think, the guys at the Cavendish actually published the first paper on this. It was received in January 1988. Ours was actually received a little bit later, 2 months later. But unlike the guys in Cambridge, we called it quantized conduction. That's better than resistance, isn't it, after all? It's different. But there you go. So what I want to say finally is John Orton, who's an absolutely splendid person. I went to work with him at Nottingham. He writes beautifully, and he and I are collaborating on what we hope will be an unbiased history of MBE. It'll come out sometime early next year, and hopefully this will put some of these stories into the literature. Okay, what I finally want to say is that things are still moving. Why did we move to Nottingham in 1991? Well, it was because the Phillips decided there was absolutely no future for the nitrides. They were dead. You couldn't dope them P-type. So that was the end of MBE at Phillips for that reason. So we moved to Nottingham, and the original intention was to grow aluminium gallium arsenide nitride as a wide bandgap semiconductor, because that's what the theorists told us at the time. Of course, it didn't. Beg your pardon. It didn't work out like that because, again, being an international effort, experiments in Japan show that if you put nitrogen into our gas, it actually narrows the gap. So that idea was dead. So then we went on to look at aluminium gallium nitride on sapphire by plasma MBE and do that work for quite some considerable time. Curiously, one of my colleagues here, Sergey, who's somewhere in the audience with all the hair, he has been very patient in growing aluminium gallium nitride substrates by MBE. It takes hundreds of hours, but you can do something unique with MBE that you can't do with any other technique. You can actually grow mixed aluminium gallium nitride of any composition. And that's led also to the work on highly mismatched alloys with collaborators here in the USA and back in Curie. Around about 2001, we started the work on spintronics, and Richard is also here somewhere in the audience. Most recently, the gallium manganese arsenide, we managed to get to about 200 Kelvin with a combination of careful growth and in situ annealing studies, but there's no way that we're going to get to room temperature. But this new material, copper manganese arsenide, which is antiferromagnetic, has an anneal temperature well above room temperature. So it may well turn out to be a very useful material. Only a couple of years ago, we started on a project on intermediate band solar cells with a Marie Curie fellow at our lab. She came from the group in Madrid. And just this year, we're starting on two new projects. One on photocathodes by MBE with a company called Photech, and one on the growth of graphene boron nitride with a piece of kit that at present is unique in the world. It has the highest possible substrate temperature, unbelievably hot, but we'll hear more about that later. Okay. A couple more things before I finish. Back in the sort of 80s and 90s, CBE became the preferred method. There were separate conferences for CBE. It died. Where's it gone to? I mean, one of the things that is curious is that if you look at a typical MBE reed oscillation, it dies after, in this case, about 35 seconds. You can prolong it by adjusting the conditions. But under the same conditions, the reed oscillations for CBE go on forever. So there's something curious going on here that we still don't understand. So there is mileage in MBE in the future. That's what I want to say. There's lots more to do. Several myths that I want to discuss finally. Okay, we heard earlier about reed streaks from Al, and it's become in the literature, it's nothing to do with Al. Al didn't make this mistake at all, so I'm not blaming him for this. You see repeated over and over again that reed streaks correspond to atomically flat surfaces. It's complete and utter nonsense. Okay? The reed streak occurs as a result of disorder on the surface. Okay? You can see this very easily if you look at a really perfect surface, as Al correctly said. The Ewald sphere cuts the reciprocal lattice rods in sharp points. If anybody ever wants to see an example of a really good reed pattern, look at a silicon 7x7 surface. It's really a whole series of arcs with sharp spots. An atomically flat surface will not give you a reed streak at all. Okay, so that's the first thing. Okay, the second thing I read in everything is MBE gives atomically sharp interfaces. Complete nonsense. Okay, when you look at the surface with scanning tunneling microscopy, it exists over 2 to 3 monolayers at the minimum. Okay, so this statement again is completely wrong. Finally, I want to introduce a complete heresy. Okay, why do we bake our systems after a reload? Sorry. Okay, the reason is historical. When we started, those cells were incredibly tiny, so the growth took place one sample at a time. You bake the system every time. The cells gradually got larger. Our growth campaigns are now more than a year. So why on earth did we spend time baking a system, making everything leak? Just grow a few layers at the beginning, clean up the system, and away you go. Okay. That's my final bit of advice. It's probably all wrong, but there you go. Okay, with that, I'd like to finish, and thank you all for your attention. Thank you very much.